All right, so we're now recording. And so chapter 2, actually start to get to work with numbers. And it is definitely arithmetic heavy. My whiteboard up here. Okay. And just double checking, make sure we don't have anybody sitting in a waiting room. All right. Now, we're going to be basically looking at two sections, chapter 2, 2A and 2B. 2A, which I assigned already. And each really, both of them together, deal with what is referred to as unit analysis. All right. And this is the process of working with units to help solve problems. Now, a unit in and of itself, when we talk about a unit, that's a quantity, and it describes what that quantity measures or counts. So, kind of a broad definition, but miles, kilometers, inches, feet, grams, pounds, and we are Americans, and we are a stubborn people. As I went through some units there, hopefully you caught that I was using, or I gave examples of what we call U.S. customary. Those would be things like miles and feet, inches. And then I also use grams and kilometers, meters, centimeters, and what is those last few terms are referred to as metric. When I was a kid in the 70s, we made a push to adopt the metric system. But again, as I referred, we are stubborn people, and we just refuse to do that. And so what we ended up with is both, and it is what it is. But that makes things more complicated. The reason the metric system, if we would have just got ourselves to a point where we would just work within the metric system, conversions are much easier. They use base 10, which is our numeration system, and it's always just a matter of converting moving decimal points. You move from a meter to centimeters, you're just moving a decimal place twice. Again, because it's base 10, just like our numeration system. So conversions are very simple. Converting within U.S. customary, because there's nothing standard about it, is fairly complicated. And because we use both, we have to have conversion formulas to move from U.S. customary to metric, and metric to U.S. customary. And there's nothing standard about it. And it can actually become quite overwhelming trying to, if you try to memorize all that. So normally we just have to have a sheet to do those kind of conversions. And because the rest of the world is metric, As I said, we're the only ones who have stuck to using U.S. customary. Um, and if of course working on cars these days is almost impossible, just because of the computerization um, and of vehicles. Um, but there's still some things I get in and do. And I have to have two sets of tools. I've got to have my U.S. customary and I've got to have my metric because it's a mishmash. And it doesn't matter if it's an American car or not because car parts are made all over the world. Um, and and so that's you never know when you get into work. You have to just figure out, okay, is this particular bolt metric or U.S. customary? Um, and so that is just the way of life. And um, so, but um, but that is what these two sections are about: is working with units and things that we see every day. Um, so, as an example, if I said, um, um, we will be working with fractions because when we talk about units, sometimes we want to talk about uh, um, rates, and that is a per. And when you hear per, PER, you've got something over something else. In fact, the most common thing we could think of as we drive our car is, how do we measure our speed? Miles per hour. Miles per hour. So that's a fraction. And if I said you were going and using some other units, 100, and I'm just something off the top of my head, 124 feet per second. All right. So now, when we're working with the units, they behave arithmetically just like if we were working with numbers. And so, in terms of how we multiply fractions and so on and so forth, it all works the same. So, how do we convert? You know, I what is 124 feet per second? In terms of I just want to have a normal idea, how fast is that? And we tend to think, in miles per hour. So that, what I'm saying is, how do I take this and convert it to miles per hour? Now, to the only thing I can multiply by and not change uh, is one, the multiplicative identity. And so I can only multiply this by one. If I multiply this by anything else, I change it. So when we're doing unit conversions, I have to think I can only multiply by one. Now, one can be written in infinitely many ways as long as the top over the bottom is the same. 3 over 3, 4 over 4, 5 over 5. So if I want to get to miles per hour, I have to think about getting the feet to cancel out as well as the seconds to cancel out. And the only way I can get the feet to cancel out is I got to have feet down in the bottom because then I could cancel the top factor and the bottom factor. Feet over feet would cancel out. So what I need to put up here is in 1 foot, so I can get my feet to cancel out. And remember, I want to get miles here. So I have to think about, oops, okay. How many feet, excuse me, I didn't mean to write that one there. how many feet to 1 mile? Now, I would not expect that you know this number. Does anybody happen to know? You can chat it in. That is, how many feet equal 1 mile? Anyone happen to know that number? Going once, going twice. All right, now there's a lot of conversions that I don't know. I have to look them up. This is just one that I happen to know. Oh, somebody's chatting it in. Yes, that is it. All right, so 5,280 feet. So it gives you a frame of reference because, again, we tend to talk in miles. This past weekend, I was in the Great Smokies, hiking in the forest all weekend, in the woods, and I don't know if any of you have ever been to the Great Smokies. It was really my first time there. I am an avid outdoors person, but in the Great Smoky National Park, um, one of the great places to get to is a mountain called Mount LeConte. Um, and there's a lodge you can stay in up there, but you have to. The reservations are really hard to get, and the only way you can get there is to hike. There are no roads, and it's 6,593 feet. So you're just right there. You're over a mile up, and so for 1 mile there are 5,280 feet. Now, again, this is equivalent. So this is a factor of 1. So it's okay to multiply by this. Now, what that sets up is, though, I can cancel out the feet, and I'm left just with miles. Now, if I'm wanting to get to miles per hour, I then also have to deal with the seconds. Now, this is one that I would hope everybody knows. In terms of conversions, if there are, for 1 minute, I hope everybody knows that there are 60 seconds, and for 1 hour there are 60 minutes. So also then equivalently, for 1 hour in terms of seconds, 60 times 60 is 3,600. So 3,600 seconds is equivalent to 1 hour. And then the seconds cancel. But notice what it leaves me with: miles over, which again is per, miles per hour. Then it's just a matter of doing the arithmetic. It would be 124 times 3,600, and then that divided by 5,280. And unfortunately, I can't have my calculator up on the screen, but you can push the buttons on that. And I'm going to right now. 124 times 3,600 divided by 5,280. Oh, whoops. And make sure you hit the right operation. I hit times instead of divide. Times 3,600 divided by 5,280. So we're going to round here a little bit. I'm going to take it to 10th place, which would be, so, and this means approximately because I'm rounding, 84.5 miles per hour. All right, any questions on that? Unit conversion. Okay. Now, um, all right. Okay, so I think what I will do now is look at a few problems. Some of you, again, have worked through um, 2A. A lot of you have not yet. And I'm just going to pull a few of those problems, and then we're going to go to 2B, which is still unit conversions and just a little bit more sophisticated problems. So let me go grab a few problems out of 2A. Okay. All right. Turn the page. Now, I'm looking at, so this is out of 2.A, or 2A. And let's say your car gets, this is actually number 4, and your car gets 23 miles per gallon. All right. All right. So, you know, we talked about, all of us drive cars, and um, most of us have a car that runs on gasoline, um, and an internal combustion motor. Um, Eventually, we'll probably, be dealing with electric, which is something different, but uh, most of us can relate to this. Now, I'm going to make a 350 mile trip. So I want to drive 350 miles. Um, and gasoline is costing, we'll say 310. All right. So what is the cost of the trip? All right. Now, so what I would want to do here, I need to get, if I know I'm $3.10 per gallon, I should have put that. So another way to write that one is dollars per gallon. Ah, shoot. I made a mess of that G. Dollars per gallon. All right. So I need to know first, how many gallons am I going to use? to do this. Now, that would be 350 miles divided by 23 miles per gallon. Now, so when we divide, we write this out, and this is just arithmetic. The arithmetic rule is take what you're dividing by, whatever it is. So right in the phrasing, this divided by this. And actually, to do the operation, we say we reciprocate. The easier word, synonymous with reciprocate, flip. So everything flips. Now watch what happens when I do that. I get 350 miles times now 1 over 23. And everything flips. So the gallon is now on top and the miles are in the bottom. But notice that sets up the miles canceling out, and I'd be left just with gallons. So it's just now a matter of doing the arithmetic. 350 divided by 23. And that's going to get me, and this is where you always want to be a little bit careful with rounding if you have to do multiple operations. What I always say is I don't round at all until the very last. So when I use my calculator, so I'm going to put approximately here, and I'm going to carry it out to a whole bunch of decimal places. 21739. Okay. So I took it out 5 places. But actually, what I would do on my calculator right here, you can see that. So you can see where I ended up at the 9. I wouldn't do anything. I would just leave it there on my calculator. I know this is just now gallons. So what I can now do is take this value and multiply it, just so we can watch how the units cancel out. That is, multiply it by the $310 number. Oh, shoot. Let me sneak in the gallons there, because this is dollars per gallon. And see how those cancel out. And I'm going to be left with just dollars, which is what I wanted to know, the cost. So, but again, on my calculator, I can just hit times 3.10. And I get, it's going to cost me, since we're dealing with money, it's always round to hundreds place. Cent, C-E-N-T is equivalent for 100. $47.17. And that is it. All right, any questions on that? All right. I'm going to do another unit conversion. This is just number 5, another simple one that perhaps you have done yourself. If I have 21 feet and I want to know how many inches is that, again, it's a matter of knowing what is the conversion. There are, per 1 foot, 12 inches. So if I have 21 feet and I want to get this to inches, there's 1 foot per inch. And this is just straight multiplication. But again, just so I can see how the units cancel, 21 feet, can only multiply it by 1. So for 1 foot, there are, oops, crap. Erase. All right. Pardon me. 12 inches per 1 foot. Now, so the feet cancel, but it's just 21 times 12, which in this case would be 252. Okay. Questions on that? So, this one is one that probably all of us have done, converted from feet to inches and so on and so forth. And, but what we don't usually think about is how those units cancel out. And that's why I wanted to really look at this problem. As we move forward and problems get a little bit more complicated, I want to always, we got to know how these things cancel out, leaving us with the desired units. All right. Hours, seconds. Zoom. Okay. All right, so let's look at another problem. Dealing with units which are not what we call linear. So when you have a linear unit, that's a power of 1. If you have a square unit, that's a power of 2. And we're talking about exponents here. And cubic units, power of 3. Square units typically will measure area. Cubic measures space. So now, if you have an air conditioner, and we're looking at particularly here problem number 9 on the homework. I'm 2A still. An air conditioning system can circulate 550. Now this is how we write it. It's going to be phrased cubic feet. So that's a power of 3. Cubic feet per minute. Right? And the word when we talk about space, so the inside of a room, so on and so forth, that is what we're talking about, a volume. Right? Now it can circulate 550 cubic feet per minute. Right? And all I want to do is I want to put this, how many cubic yards of air can it circulate per minute? All right, so this, I've got to be a little bit careful. Thinking about units here. If I have 1 yard, how many feet? And this is a U.S. customary unit. And that would be 3 feet. There are 3 feet to 1 yard. Now, since I'm dealing here with cubic feet, I need to think about then how many cubic feet are there in 1 cubic yard? And so what I do is I cube both sides. That is, raise each side to a power of 3. All right, exponent rules. if you have two things multiplied, and we've discussed earlier, if there's no symbol in between, that's multiplication. So I've really got two factors here, each being raised to a power of 3. So this would be 3 to the third times feet to the third. Now, 3 to the third is 3 times 3 times 3. 3 times 3 is 9, and 9 times 3 is 27. So this is 27 feet to the third, what we just call cubic feet. Now, 1 to any power is 1, because 1 times itself is itself. So it's 1. So 1 cubic yard is 27 cubic feet. Okay. So now I'm wanting to put this in how many cubic yards per minute. So I need this feet cubed to cancel out. So this is where I'm thinking about how do I get that accomplished. And I want to put this in cubic yards. So 1 cubic yard is 27 cubic feet. Now I get my cubic feet to cancel out. And so this really becomes 550 divided by 27. And that's about, to 1 decimal place, 20.4 cubic yards per minute. All right, so still just always a matter of multiplying by 1, but you choose how you arrange the top and bottom to get your desired units to cancel out. And and then the other thing on this one is when you're dealing with square units, cubic units, always be careful on your conversion factors. Any questions on this one, number 9? All right, I'm going to do one more from 2A.
Chris, I do have a question. Can you go over one more time how you took the 3 feet and converted it to the 27?
Okay. So this problem dealt with cubic because you're dealing with a volume. And so when I started with, I was given 500, an air conditioner could circulate 550 cubic feet. So, which means when you hear that term cubic feet, that means the units are to the power of 3. That's an exponent here per minute. And I wanted to get this to cubic yards. So when I'm thinking about, again, either cubic feet because I'm dealing, or a cubic unit because I'm dealing with a volume, or a square unit, I have to be careful on those conversion factors. And so what I first start with is there is 3 feet to every yard, 1 yard. Then in order to figure out how many cubic feet are in 1 cubic yard, the way I get there is on this equation right here, I raise each side to a power of 3. Now, so this deals with just this arithmetic idea. How do I raise powers? Or what is that? So this is 3 to the third. And what is 3, what is an exponent? Exponentiation is to multiplication, just like addition is to multiplication. That is, it is a shortened form of, it says take the base and multiply it that many times, whatever that exponent is. In this case, that's 3 times 3 times 3. And so multiplying this all together, 3 times 3 is 9, and 9 times 3 is what? 27. And you do that to both sides. So that's where I got my 27. It was 3 to the third. And then you also raise the units to that same power. And now 1 to any power is itself. So it doesn't matter. 1 to the 100th power is still 1. Does that help?
Yeah, it helps me. And then I'll watch the video about a dozen times too.
All right. So remember, when you are dealing either with square units or cubic units, to first take that conversion factor where their power is 1, and then raise each side to either the power 2 or power 3. Hold on one second. Okay. All right. Sorry, the email came in from the president. I just looked at it real quick. All right. But yeah. And so if you're in the 120E course, that's why there were some problems just dealing with exponentiation. So, all right. And then once I've got this, then I can actually come in and do the unit conversion. All right. Now I was going to go ahead and do one more. This deals with currency. So again, another example where you do conversions all the time because every country has its own monetary system. We use US dollars. If you're in Europe, you've got euros. If you're in England, they pretty much stick with pound. That is their unit. If you are Japan, it's the yen. I'm just throwing out some examples as I can think of them. This particular problem, number 11, deals with Mexican currency, which is peso. So they give you 2 conversion factors on number 11. That is 1 peso is 0.07644 dollars. Okay. And $1 is 13.08 pesos. Okay. So so you would come out of Mexico and you've got yourself 3,400 pesos. So the question is, how many dollars would this be worth? So if I think, well, I need to get the pesos to cancel out, then I will multiply this by 0.07644 dollars over 1 peso. And I choose this so I can get those to cancel out. So if I If I had dollars and I wanted to know how many pesos, I would have used this one. And then it's just a matter of actually 3,400 times that. And again, that's where we want our calculator. So 3,400 times 0.07644. And so we're going to be, and again, it's dollars. So 259, round to hundredths place. In this case, round to 90. In the calculator, you get 0.896. So rounding to hundredths place would round to 0.90. Any questions on that one? Okay. Now on 2B. There were originally, I was going through it this morning, 22 problems. I have actually shortened that down to 15. So I eliminated 7 problems in an effort to try to ease your workload a little bit. So it's down to 15. But it is much more involved. Looks like it gets a little bit more sophisticated. Now, so we're looking now at section 2B. The title of this section is called Extending Unit Analysis. So again, just looking at more sophisticated problems of solving problems which involve converting units. And a couple of tables, which, you know, if we were in the classroom, I used to just go get on the copy machine and print this and get a copy, then just make a hard copy print for everybody. Not really an option here, but everybody can get into the e-text, which is our textbook. And so this is a table you want to go in and have handy, which is on page 89, and it is table 2.2. And it deals with U.S. customary and converting to metric and the conversions. And I mean, there's a whole bunch dealing with lengths and weights and volumes, all kinds of them. I'm going to attempt to kind of show you here. Everything works backwards. And you can't quite see all of it. I can't put the whole thing in the frame, but there's a good bit there. And that is a good reference to have. Now, I in no way would expect you to have those all memorized. That is, you can reference those as needed per problem. And but as an example, for 1 inch, there are 2.5 centimeters for every 1 inch. It's always in my Math 121, which is an education class a content course, mathematics for education majors. little section where we're wanting to just collect data because we're wanting to actually talk some statistics, which we will do later this term and work with some statistics. And so I show them a real simple way to collect some quick data instead of just using data canned out of a textbook. And I'll hold up a piece of string, which I don't think I have a piece of string here handy, but some piece of string which I know the link to, and I'll hold it up. But before I hold it up, I'll say I'm going to hold this up and just for a couple seconds. I want you to look at it and then jot down in inches how long you think it is. And we'll do that. And I'll go through and get everybody's numbers. And of course, there's some variance to it. That is, not everyone has the same answer, but they're relatively close. And then I'll say, now, nobody use your calculator. No one Google it. Don't Google, and because you can Google up conversion factors on, and have Google actually do the conversion for you. But so just your best estimate. But I want you to estimate it in centimeters, and I bank on it. That there's going to be a lot more variance. I mean, we're all over the map. And so statistics, one of the things we initially do is talk about measures of central tendency. Where's the middle of the data, numerical data, and then how much variance is there? That is, how much spread per se is there? And you get a lot more spread with that. But the actual conversion factor is to take your inches and multiply it by 2.54, and that gives you your centimeters. And so this table 2.2 does both converting from U.S. customary to metric. It also deals with just working within U.S. customary. Like, it has 1 foot is 12 inches and 1 mile is 1760 yards or 5,280 feet, so on and so forth. Deals with weights. All kinds of units sometimes that we don't even know or think about. Pounds, we do know, that's 16 ounces. A carat is 0.2 gram, or it's 3.086 grains. And again, I'm just throwing a few that I'm looking at here. A quart is 2 pints, which is 57.75 cubic inches. 1 barrel of petroleum. We love to talk about barrels in terms of, you always hear, what is the cost per barrel? But that's 42 gallons. A bushel is 4 pecks. It's not one I did, but 1 cubic yard is 27 cubic feet. It's right there on the table. But if you get in the e-text, you can look up page 89 and you can see the table, and for yourself, do a screenshot of it, have it and save it, as a file on your computer and use that. Another table on just 2 pages over, and it is table 2.3, and it deals with just metric, right? And on this one, this deals with how and again, metric is powers of 10, just like a numeration system. And it deals with all of them. So if you start out with your, just like, say, a meter, then a decimeter, and the way the table reads is you'll have deci, an abbreviation is a small d, and it says the value of it is 10 to the negative first. Now, negative exponents. What a negative in the exponent means is reciprocate. It doesn't mean the value is negative. It just says reciprocate. That is, 10 to the negative first is actually 1/10. 10 to the negative second would be 1/100th, so on and so forth. So if I had a meter, 1 meter, then would be, I would move the decimal point back to the left in that direction. Negative would indicate go that way, and that would be 0.1 decimeter. And then it would work exactly the same way if we were dealing with not meters, but say liters, measuring liquid. Or if I was measuring a weight in grams, 1 gram would be 0.1 decigram. Now, likewise, 1 meter then would be 0.01 centimeter. So on and so forth. It's always just a matter of moving a decimal point. All right. So again, another very useful table. And again, this one just has all kinds of conversions, both again within U.S. customary and U.S. customary to metric. This table deals just with the metric system and in terms of the words. Okay. And then on page 93, table 2.4, these are U.S. customary to metric. They're all U.S. customary metric. That is 1 inch is 2.454 centimeters, 1 foot, 0.3048 meters. That one definitely doesn't stick in my head, but I can use that, and when I need to make that kind of conversion within a problem. Okay. And then again, what we're really looking at doing is looking at problems that are a little bit more sophisticated, dealing with unit conversions, or what we'll call unit analysis. Temperature conversions. There are three types that we use: Fahrenheit, Celsius, Kelvin, and converting within those three. Not sure that there's actually any temperature conversion problems within the homework set now. Dealing with units describing energy, and then subsequently power. That is, so what is the difference between energy and power? Energy is what makes matter move or heat up. That is energy. And the international unit, metric unit of energy is called a joule, Joule. Power then is the rate at which energy is being used. And that term, the unit we use to describe energy, is called a watt, W-A-T-T. All right. So again, energy is what makes matter move or heat up. Power is the rate at which energy is used. And energy is measured in joules, Joules. So joule is the unit which measures energy. And a watt is unit of power. And 1 watt, since again, a watt is measuring the rate, and when we're talking about rate is going to be per unit of time. So a watt is defined as 1 joule per second. Okay. Okay. Now, so example problem dealing with energy. So you jump on your bike. Let's just say it's an exercise bike. So you're what we call a stationary bike, or what I like to call a ride on the wheel. And display states that you are using 500 calories per hour. Now, calories is a measurement of energy. So 1 calorie is equivalent to 4,184 joules. All right. Now, so this says this again, you're on your exercise bike and you are using 500 calories per minute. And I'm going to make that a little neater. Per minute. All right. Now, question. So this is how much energy that we are using here to ride our bike. Now, are you generating? Excuse me. This is your power that you're using here. Now, are you generating enough power to light a 100 watt bulb? Now, so I'm going to put here power used to ride bike. So the question is, are you using enough power, generating enough power on the bike? If this is the power you're using to ride the bike, to light a 100 watt bulb. Okay. All right, so what we need to get, if I want to know if I can use enough to light a 100 watt bulb, I need to get from calories per minute to joules per second. So remember, joules per second is what? Equivalent to a watt. And so since I need to know if I can power up this 100 watt bulb, am I generating enough? I need to get this to joules per second. So this is where, kind of like doing the miles or the feet per second that I initially did today to get it to miles per hour. I'm going to do this same kind of unit conversion where I just kind of carefully make sure I get my units to cancel out. So it would look something like this. And kind of running out of room. Let's see if I can pull this off. Calories per minute. Now I want to get to joules per second. So first off, I would need to get to joules, and we'd already stated that somewhere on the right here, 1 calorie is 4,184 joules. So 4,184 joules per what calorie? 1 calorie. but that gives my calories to cancel out. All right, so I've got that. Now I've got it to joules. Now I need to what? Get to seconds. Now, so I'm in minutes right now, and I know that there is 1 minute per what? 60 seconds, and that gets my minutes to cancel out. Now I'm down to what? Joules per what? 60 what? Seconds. All right. And oops. I may have. Oops. Yep. Okay. I thought something was amiss here, and I apologize right from the get go. Your bike was you burn. Now, this is, I'm going to use, I made a little mistake when I initially set this problem up. And some of you may have caught this or kind of raised an eyebrow like, wow. But I'm going to use this as a point of, in a more general discussion that I haven't mentioned yet, that the most important thing I want you to walk away from this course with, and that is what I call numerical sense. And I didn't have my numerical sense operating here as I started to set this problem up. I threw a number out, this rate of 500 calories per minute. Now I want you, and where I'm going with this is the ability, when I talk about numerical sense, you hear a number, a rate given, and you just know immediately that's not possible. It doesn't make any numerical sense. Some examples that I have seen in my career. These are answers on tests, and it's just like, I'll give a point if you just say, I know that the answer I came up with just doesn't make any numerical sense. Airplanes do not fly at 5 miles per hour. You need at least, for a commercial jet, you've got to get at least 170 to 180 miles per hour just to start to achieve lift and get that plane off the ground. 5 miles per hour is not going to get it in the air. Other examples that I have seen, distances are not negative. I measure out a distance. It is a positive value, or at least non-negative. It could be 0, I suppose. You could not move at all, but it's not negative for sure. My favorite nonsensical answer ever given was not even my test. This was just my original boss when I started working here 29 years ago to college. He was a biology professor. He was the chair of the department of the division, the science division at that time. He was late. He was a great guy, but he's passed away. His name was Gary Wagner. Taught biology here for years and years and years. Anyway, he told me on a test question, the biology test was, what was the gestation period for a pig? Which I still did. I've been told the answer, then it's like a number that won't stick in my head. But anyway, a kid answered 9 years. That was his answer. I don't know what it is, honestly. I always forget. I could guess and get a lot closer than 9 years. Just, it does not, a gestation period for a pig it's like, pig does not carry its baby for 9 years. Again, just not numerical sense there at all. Another one, this was from a trig class. I want to put a 400-pound box in the back of my truck. And so what I do to help me out is I put a ramp, what we would call mathematically an inclined plane, at such and such angle with the ground. it decreases the amount of force you need to apply to the box. And so there's, you don't have to know the trig here, but there's, some trig involved. You take your angle that the inclined plane makes with the ground and do some trig, and then you come up with the amount of force you need to apply. So remember, it's a 400-pound box, and here the answer is 620. Again, just not numerical sense. If I lift the box straight over my head, the most max force that I'm going to apply is 400 pounds. It's 400 pounds. I can't apply anything more than what the box weighs. The reason you put the inclined plane there is to decrease the amount of force you need to apply. It has to be a number less than 400. All right, so getting back to what I just did, boy, it would be great if we had an exercise bike that burned 500 calories per minute. That, well, it would kill us. On an average day, most of us average about intaking about 2,500 calories. If you could burn 500 calories per minute, you couldn't possibly eat enough to keep up with that. You would shrink to nothing. This should have been calories per hour, and I apologize. I should have caught that immediately, and I did not. So that, sorry, I'm running off my tablet. That is a reasonable number. All right. So again, I wanted to get this to joules per second. That didn't change. But it was originally calories per hour. Oh, man. Per hour. Oh, my gosh. Sorry, I keep running off my tablet here. Calories per hour. So I got the 1 minute over 60 seconds. And then there are I need to get the hours out of here. So let's just back up here. All right. So I dealt with my calories, got them to cancel out 4,184 joules. Now I need to take care of the hours and get the hours to seconds. So in 1 hour, there are 60 minutes. And then in 1 minute, there are 60 seconds. Then I can have my hours cancel, and I can have my minutes cancel, and I'm left with joules per second. And so it'd be a matter of getting your calculator. So I got all my units to cancel out accordingly, and then I could go 500 times 4,184 and just divide that by 3,600, which would be 60 times 60 down here in the bottom. And that comes out to 581 then joules per second. Now, which means that's 581 watts, because joule over second is watt. So yeah, it's enough to power almost 6 light bulbs. If you you're pedaling enough to generate enough power to almost light 6 light bulbs. Okay, and I apologize for writing in a calories per minute there. Again, I just was kind of flying through the problem, and I did not think that was, again, not a sensible number for that rate. Any questions on that example there, talking about energy and power? Okay. All right. B. All right. So in the homework of 2B, there are 15 problems again. It starts out with problems that deal with what is energy, and number 2 talks about just basically what is the difference between energy and power, which we discussed. All right. And then number 3 deals with energy and power. Then number 4 deals with question, decide whether this statement makes sense. The beach ball we played with has a density of 10 grams per cubic centimeter. Now, and I'm going to, so this is dealing with number 4, but in terms of density of water, it is 1 gram per cubic centimeter, and this is density of water. All right. Now, so the statement, the beach ball we played with has a density of 10 grams per cubic centimeter, wouldn't make much sense here. That would make the beach ball not only not float on the water, it would sink. And I'll help you out with number 4. All right, and so then from the rest of them, it just deals with unit conversion problems. Again, on each one, you'll be able to go in and look at an example to help you work through it. I think I'll go ahead and at least look at one here. One like that. Car problem, which we've done. Lots of light bulbs. Look at that. Okay. All right. Well, all right. So I'm going to look at one problem from here. This is going to be number 5. Again, this is 2B. And the problem is you're filling up a hot tub. And A hot tub can fill at a rate of 1.7 gallons per minute. How many hours would it take to fill a 240? So how many hours to fill a 240-gallon hot tub? Okay. So the first thing I would look at in doing this problem is I'm dealing with units of minutes. So I know I'm going to need to get that to hours. So we're going to have to convert that to then gallons per hour. And so I could take my 1.7 gallons per minute times 60 minutes for 1 hour. So I get my minutes to cancel. Now I'm gallons per hour. And then 1.7 times 60 is 102 gallons then per hour. Now, again, I'm wanting to know how many hours to get this thing filled up. So I know I'm at 102 gallons per hour, and I want to fill a 240-gallon hot tub. So that's where I'm going to say 240, then divided by 100. Put the units in there. 240 gallon hot tub divided by 102 gallons per hour. Now, so again, remember, if I'm dividing, flip and multiply. So that's going to be 240 gallons times 1 over 102 hours. Per gallon. Get some gallons to cancel out. And it's just 240 divided by 102. I'm left with the units of hours, which is 2.35 hours. And that's it. All right. Okay. So what I'm going to have, I'm going to assign 2.B. And there is also a quiz going over sections 2A and 2B. I'm not going to, I'm going to assign the quiz later today. And then we're going to have a test that I'm going to assign over chapters 1 and 2, which I'm going to be looking at assigning that test on Monday. But I want you to, so basically, I want you to finish through the weekend working on problems through chapter 2. On Monday, I want you to bring test or questions from any homework questions. And I would anticipate you're going to have a few, especially from 2.B, dealing with the unit conversions. And then at the conclusion of those, and you can also bring questions from the quizzes as well. I will then assign that test, and we're going to march on into chapter 3 at that point. I'm going to then sign this. I'm putting a due date of Sunday. for both the homework of 2B, which I just assigned, and I will also put Sunday for that quiz. But I want to, let me go in here real quick and just get a look at it. Sure. Yeah. Okay. We're good. I can go ahead and assign it. So I've signed the quiz, and then I will look for questions on anything from 2A and 2B. And then I'm going to assign the test over chapters 1 and 2 on Monday is the plan. So any questions? Okay, I'm going to go ahead and